Hey everybody, and welcome back to Linear Algebra Online. So today we're going to really jump into what is some of the most important content in this new unit. And I want to start off and just kind of do something that might be kind of obvious, but also really important. So this set right here is what we call an orthogonal set in R3. So these three vectors are perpendicular. They're kind of like an I hat, j hat, and a k hat, right? And to show that they're orthogonal, mathematically, just the way that you can do this is take any like arbitrary v sub I and dot product it with v sub like j, like a different one, right? And that better equals 0, right? That's kind of the main idea, right? Any of these should dot product to 0. So we can just go through, do v1 dot v2, and we would get 0 plus 1 minus 1, which is 0. Then we could do v1 and 3, and we would get 2 minus 1 minus 1, which is 0. And then v2 dotted with v3 is 0 minus 1 plus 1. So that is literally shows it, right? Any arbitrary vector in this set, if you dot product with another one, you get 0. Really the idea with dot producting and getting 0 and why that's perpendicular is like if you have a vector, right, and you've got some perpendicular vector to it, what dot product is really doing is it sort of like checks how much of this vector shows up on this vector. And so like if you squish this vector down, right, it kind of smushes down to 0. And that's kind of a more conceptual reason why it's perpendicular. I'm saying these are perpendicular, gets you 0. But you can also just think of it with the like cosine sort of definition of dot product, right? Like cosine of theta is like u dot v over magnitude u, magnitude v. This kind of thing that you learn in Calc 3 is just another reason why it works, because we know that like cosine of 90 or pi over 2, right, is going to be 0. And if you have a fraction equals 0, this part has to be 0. So, yeah, and this is really what, I said this in the last video, but this is really what we're kind of building to in this video, or in this unit. We want to basically be able to find sets of vectors like this that are perpendicular, and it gets much harder when you have much bigger sets, and you may have, 5, 6, 7, 8, 9 different vector, like a different dimensional set, and you want to be able to get a basis for that set, and finding an orthogonal set for R7 can be really hard, but it turns out that there's a very algorithmic way that we can do this if we just know a little bit of linear algebra. So, all right, so there's two important properties I want to just talk about quick for orthogonal sets, and that's, again, any one where you dot product any two and you get 0, when these are not equal, I guess. So one is that the set is linearly independent, and there is a proof in the book, but I'm not going to worry about proving that here because I think it's pretty intuitive. The other one is maybe not so intuitive, and I do want to prove that one. So this one says that if you have a set V1 through Vk, that's an orthogonal basis for the subspace W of Rn, and we're going to let W be any vector in that subspace, then the unique scalars C1 through Ck, which such that W equals, this is the linear combination of that basis, that the C's are given by this specific dot product kind of formula here. So to prove this, first off, we know that they're, I guess I'll say it like this. So if there exists this basis V1 through Vk, and W is like a subspace inside of Rn, so there exists this set V1 through Vk for Rn, so it's acting as a basis for Rn, and W is contained in Rn, then we know just by like our definition of a basis, basically, that W has to equal some linear combination of those vectors. So that's like the first part, is that there exist these kind of scalars, okay? And then we have to just show the computation part for it, so how we get this specifically, okay? And to do that, so what I'm actually going to do is I'm just going to compute W dot V sub I, okay? So W is this thing, right? So I'm just going to pop that in. So C1 V1 plus blah, 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 plus CK VK. So this thing, right, is dotted with V sub I, right? And so then from that, we could get that we can like distribute that dot product. And so we're going to get like C1 V1 dotted with V sub I. Then we'd get plus a bunch of things in here. And then we get CK VK dotted with V sub I, right? And we know that since this is an orthogonal basis, right, like this is happening whenever these subscripts are not equal, right? So this one actually goes to 0 and this one goes to 0. But in here, right, somewhere in that like string, right, I got to a point where it was V sub I was in there, right? And I dotted it with V sub I. And we know that this one would be, oh wait, no, I don't want that, sorry. Let me undo that. So all that matters is that somewhere in there, there's going to be one that, I was about to say it goes to 0, but then the whole thing would be wrong. But this one doesn't go to 0, right? We know that the other ones go to 0 in there, but this one would just sort of stick around. So most importantly, what we got now is that W dot V sub I simplifies way down to C sub I, V sub I, dotted with V sub I. And you probably see where this is going, but if you just literally divide out, right, C sub I would equal W dot V sub I over V sub I dotted with V sub I. And that is what we wanted to show. So I'm going to do a little box, and we're done. So that's just like a nice way that we can actually compute, like, no matter what basis we have a very concrete way to now compute the coefficients, which, if you think about it, is really handy, because a lot of times before we would have to do some sort of matrix row reduction sort of argument in order to figure out like how much of V1 plus V2 plus V3 or so on you can add together to get W or some vector, right, in the space. But now we know that we don't have to do any matrix computations. We just literally have to do two dot products, one on top, one on bottom, and that is the amount of V1 that you need, and then amount of V2, V3, and so on and so on. This is a very, very quick and efficient way to get W. It's kind of the first example of why orthogonal sets are nice. This is very much a product of just orthogonal sets. All right, so I want to actually do that for a concrete example now. So what I'm going to show you is, so V1, V2, V3 are drawn over here. I think this red one is V2 because it has 0 in the like K direction or Z direction, right? And then I think this purple one is V1. Doesn't really matter too much, but and then this one is V3. And so what I'm going to show you is, so I can find W as a linear combination of these vectors, right? And I can do it just with this computation thing that we just saw on the last slide. So, so you don't have to do any row reduction or anything, which is how we had to do it before. And this is an orthogonal basis, which is important, okay? So to do this, basically we're just going to do this kind of thing 3 times. So, the idea is, again, just W equals C1 V1 plus C2 V2 plus C3 V3. And I'm just going to find C1, C2, and C3. So C1 is W dotted with V1 over V1 dotted with V1, okay? Which is just going to be, 2 plus 2 minus 3. This is the kind of math that I'm so bad at. This is going to be 4 plus 1 plus 1. And so if you do that, you get a 6, I think. And then keep doing that. C2 would look like W dot V2 over V2 dot V2, which is going to be 0 plus 2 plus 3 over 0 plus 1 plus 1, which is 5 halves. And you do the same thing for the last one. C3 would equal, I'm just going to tell you, it's 2/3. You just do W dot V3 over V3 dotted with itself. And so what this means is, we now know our C's, 1s, 2, and 3, that we have in here that we need in order to build 1, 2, 3 out of these vectors. Computationally, this is much easier than doing a massive row reduction problem. And I could kind of show that a little bit, but basically this is the combinations. This is like the 1/6 of one of these plus 5 halves plus the other one, 2/3 the other one. If you do that out tip to tail, you'll get the green vector, which is 1, 2, 3. That's the idea. So there's actually another way that you can write this kind of thing. And it's something that actually shows up earlier in the text, but I always wait till this point to talk about it. And it's this thing. So if you have a basis, like V1 through VK, and there's some subspace that you have in there, so this is a basis for that space, sorry. V is a vector in the subspace. V then can be written as a linear combination of that basis, right? And there's a technique, a notation, I should say, where we do little brackets around the vector V, and we write kind of a script B typically, and then we do so C1, 2, 3, all the way down. These are what we call the coordinates of V with respect to that basis, okay? And it seems kind of weird, but it's actually quite important when we get to something called change of basis. So change of basis is going to become a very important thing, because what we're doing in this whole unit is, if I go back to this thing, we're basically going to recreate a basis for a space we already have. Like we might be finding V1, V2, V3 for R3, and so it's going to change the coordinates of certain vectors because of that change of basis we have. Now, just to kind of show a connection to something you already know, like if you have the standard basis, like E1, E2, E3 is like I hat, J hat, K hat for R3, then if you were asked to find the coordinate vector of like V equals 2, 7, 4 with respect to that basis, then what you do is you just say like V with respect to the standard basis E, and is just 2, 7, 4, because there's nothing to change, right? But there's definitely times where it can change. Just for example, here I'll do another one. So say you have this basis. So if you have U and V, these are basis vectors for some plane in R3. There's a vector W, okay? So W, which equals 0, 5, negative 1, that is a vector in the plane that's spanned by these two basis vectors, okay? And so what we could do is we could say, like, all right, some basis is defined by the set of U and V, and W here equals 2U minus 3V, which isn't probably too hard to see. And so then what we can say is W, and we put in little brackets, and we do a little script B, because that's how I'm labeling my basis, will equal the vector 2, -3. So sometimes it can totally change it. Like here you took a three-dimensional vector in R3, but we are describing it as a two-dimensional vector because it is described now fully in terms of the two-dimensional plane that cuts through the origin in R3 and stuff. So so it's not always as trivial as this. In the last example, okay, the amount of vectors that I have here fully still describe and span R3. So when I do when I write this as a coordinate, the coordinates of W with respect to my new basis here, it'll just change what these entries are, because 1, 2, 3 was in regards to the standard basis, but I don't have the standard basis anymore. I have a different basis right here. And so if I say, let's say just B, script B again, is the set V1, V2, V3, right? Then W with respect to this basis is going to be 1/6, 5/2, 2/3. So still a 3D vector because I still have three vectors spanning all of like R3 space here. But the coordinates have changed based on that, those new basis vectors, right? Whereas you needed, 1 of I hat, 2 of j hat, 3 of k hat before. Now you need 1/6 of V1, 5/2 of V2, and 2/3 of V3. So this is an important kind of notation that you'll see a lot actually from this point on in the book. Oh, and that's where I was going to write it before, but anyways. So one just kind of important change to that last slide right here. This one. If I amended it just a little bit, okay, and I changed the word orthogonal basis to orthonormal basis, which is an orthogonal basis, but now where everything is length 1, this is like I hat, j hat, k hat, the standard basis, then realize that this part right here, if this was orthogonal, right, this is going to actually reduce, and each c sub I is just going to be w dot v sub I over 1, right, which is w dot v sub I, v sub I. And computationally, this is even easier than before now. So it was already easier because we could do things like find this coordinate vector without doing any row reduction and just literally doing dot products, right? But you can imagine that if these vectors here were length 1, it would save us this work on the bottom, right? So computationally, that is even easier, and this is sort of what we strive for the most when it comes to a lot of like computational mathematics problems. And so this will be the thing that we're building towards as we go in the unit. And it takes some time to kind of get there, but ideally we have orthogonal set that is also length 1 because it, this is just another example where the coordinates of the vector become just w, whatever the vector is, dotted with whatever vector you've got for that entry, right? The first one, second one, third one, so on, so on. So easier, definitely. All right, so I want to do a little proof here. So this is a very important theorem, and it says that the columns of an m by m matrix Q form an orthonormal set, Okay, so one of those perpendicular and length 1 sets, right? If and only if Q transpose times Q is the n by n identity, right? Notice too that computationally you can definitely do this, right? It's like, you know, if Q is m by n, this is n by m, and so then you have an n by n identity. I always felt like m's and n's were too close for linear algebra. I wish they did like P and Q or A cross B or something. But anyways, so you can definitely do this computation. And what this is saying is that you have an orthonormal set if and only if this happens. All right, so I'm going to start off and prove the forward direction here. And so I am just going to basically assume the columns of Q form an orthonormal set, and then show that QTQ is I sub n, okay? And so I'm going to just start off and say let lowercase q sub I, that like vector, basically be the ith column of Q, all right? So Q's, well, I'll just say so it will also be the jth, we'll say, column of QT, right? And just because of like how Q and its transpose would work, right? So then we know that if we just do QT Q, right? Basically just like the I by J, like I rows, well, what I really want to say is not, so I want to say the IJ entry in this matrix multiplication is coming from the ith row of Q transpose, right, and the jth column of Q, right, then I know that this really just equals, and if you just do matrix multiplication with the dot product, right, you get Q sub I, right, ith row of Qt dotted with Q sub J, the qth column of, the jth column of Q. So I basically am just doing, basic matrix multiplication, rows times columns. And we know that this thing, right, will equal 0, right, if these two things are not equal, and that's just because they're perpendicular, right? And it'll equal 1 if I equals j, and that's because they are normalized, right? They're length 1. So if you think about what this means, right, then it's basically saying that QTQ would equal, here's an entry where I is equal to j, so you get a 1, but here is not, and here is not, and so on, right? And then here is not, but then here is 1, and then here is not, and then so on, and so on, and so on, right? So on, and so on, and so on. And it just keeps doing this, right? And you get, this nice structure like that. Well, really, I should have kind of messed that up. So we'll go da-da-da-da-da, and then 1, and then 0, 0, like something like that. But you get a nice identity matrix, right? And it's an n by n identity matrix based on just the sizes of Q and Qt. And the nice thing about this proof is actually everything is reversible. So the if and only if part comes out very nicely, because you can basically just, I'm not going to write it down for time reasons, but basically if you started here, if you had this, right, then you can say, well, this matrix multiplication is just built out of these specific dot products of the columns and rows, right? Rows of QT, columns of Q. And so then you can like backtrack and say like what it's saying about, each of these dot products. And if you're getting that, right, then that is what it means to be orthonormal, right? And so you can just kind of do this whole thing forwards or backwards, and it proves the if and only if, which is nice. All right, so this is the last kind of thing I just want to point out. So this is a very important theorem, basically just, again, saying that the columns of an n by n matrix form an orthonormal set if and only if you get this nice result, okay? And an n by n matrix Q, whose columns form an orthonormal set, is called an orthogonal matrix. And this always bugged me in math, okay? But basically, the square version of that previous problem is called an orthogonal matrix, and it really should be called an orthonormal matrix, but it's not, okay? They call it orthogonal, but if it's the square matrix version of this problem, all right, so you still have the orthonormal part, still the length 1 going on, they only call it orthogonal matrix. They don't call it an orthonormal matrix. I don't know why. And the really important thing I want you to notice here, so if you have the square one, right, then you can talk about inverses, okay? And the nice thing to notice here is that if you go here, right, if these matrices are square, then QTQ equaling the identity, right, implies that the transpose is the inverse of the matrix, right? And in fact, a square matrix Q is orthogonal, or orthonormal, whatever, if and only if the inverse of the matrix is the transpose of that matrix. So this is another crazy nice computation fact, because you can actually take a matrix and you can just check its transpose, which is way quicker than checking its inverse. And if the transpose is equal to the inverse, so you still need to, I guess, check both, sorry. But if those are equal, then you know that they're orthogonal. Or I guess what I was sort of thinking before is if you know the columns of the matrix are orthonormal, then you don't have to go through the computation of the inverse. Then you can just get the computation of the transpose to get the inverse. So just to show you kind of here, if this is my like 2 by 2 rotation matrix, right? So the transpose is just going to be cosine alpha, sine alpha, minus sine alpha, cosine alpha. And if we just do rows times columns, notice you get cosine squared alpha plus sine squared alpha in the first entry. Then you would get cosine, I think I have enough room, cosine sine minus cosine sine, right? Then this entry, you would get sine cosine minus, where is it? Cosine sine. And then this one would be another sine squared alpha plus cosine squared alpha. And so truly, this goes to 1, this goes to 1, this goes to 0, this goes to 0. And you're getting the identity, which is pretty cool. So if that happens, right, then we know that these columns are basically orthonormal, which isn't surprising because we kind of know that we've talked about the construction of that matrix before, and we built them that way, being orthonormal. So just kind of a cool link into something we've seen before, but very, very handy kind of definition and theorem to know here.